to be by Carolina Benone from the Universidade Federal do Pará in campus de Salinas, and she's going to talk about Ergoregion instability in a fluid with vorticity. So the floor is yours.
Thank you, Antonio. Good morning, everybody. For me, it's always a pleasure to be here in Belém and talking to you. So today I'm going to talk about this work that was done in collaboration with Leandro Oliveira, who is also from the campus of Salinópolis, and Luis Crispino, who is from the campus of Belém. You all know him. And it has been recently accepted for publication in Physical Review D. So to me, one of the most intriguing solutions of general relativity are the solutions of black holes. And at the beginning, when these solutions first were discovered, the scientific community thought that they were just a mathematical curiosity, and you shouldn't be able to have something this strange in the universe. So you shouldn't be able to form or to see something this strange in the universe. But nowadays we have a lot of evidence of the existence of these objects. We have evidence that comes from the fact that they have in the environment. We have the detections of gravitational waves. Up to the end of the third run of observations of Virgo, LIGO, we had 90 signals of gravitational waves that are consistency with black hole binaries, neutron binaries, and black hole neutron star binaries. Neutron star binaries and black hole neutron star binaries. And we also have the images of the black hole in the center of our galaxy and the center of the M87 galaxy. So all of these observations, plus the theoretical advancements that we had, they point that they are very strong evidence of the existence of black holes. However, there are still challenges in proving the existence of black hole. In particular, when we consider, because a black hole is characterized by its event horizon. So to prove the existence of an event horizon, it's a very complicated thing to do. So it's been a few years that we have a lot of different propositions for other objects that mimic various aspects of black holes, but that do not possess an event horizon. So we have ultra-compact objects that can mimic many of the characteristics, but do not have an event horizon. Okay, so when we consider a rotating black hole as, for instance, a Kerr black hole, we know that it possesses an ergoregion, which is a region where everything, nothing can stay still, and everything must rotate in the same sense of rotation of the black hole. And at the ergoregion, you can have modes with negative energy. So if you consider a scattering problem, so if we consider a wave impinging on this black hole, then if it has a low enough frequency, then this mode can be superradiant, can be amplified by the black hole. So you have an incident wave, but the reflected wave has a larger amplitude than the incident wave. And this plus in the energy of the reflected wave comes from the black hole. So this wave can steal energy from the black hole. If we put a mirror around the system, now we have a way for this superradiant mode to be amplified again and again and again, and you can create an instability which was proposed by President Tolkowski and was named the black hole bomb. So you can have this amplification occurring again and again until the system, this mirror cannot sustain this radiation pressure, and this energy is released all at once. If we now put the mirror inside the ergoregion, Now we can have another kind of instability. So now these modes, they can leave the ergoregion with a positive energy and leave by conservation of energy. We can show that we have modes with even smaller energy inside this ergoregion. So if this process keeps happening, then we have what is called the ergoregion instability. And so you keep stealing energy from the system until you don't have an ergoregion anymore. So this was studied by Friedman in 78. And this type of instability can occur for any system that has an ergoregion but which does not possess an horizon. So this was studied, for example, by Oliveira and others for the case of the hydrodynamic vortex. So in order to study black holes in the laboratory, Unruh proposed a model in 1981 where he showed that a perturbation in a fluid can see an effective curved spacetime. And in particular, you can form an event horizon, in this case, an acoustic horizon, when the velocity of the fluid is equal to the speed of sound. So this is what we have here in this red line. And this model of Unruh was also studied for considering rotation by Visa. But both these works considered only a rotational fluid flow. But more recent works have considered the effects of the vorticity in the spectrum of the solutions. Okay, so we are interested also in studying these kinds of this ergoregion stability, but now we will consider a fluid with vorticity. So this omega zero is the vorticity of the background fluid flow, and we by substituting this in the equations, in the fluid equations, we find this differential equation that we have to solve. And for the background velocity, we consider this expression. So we have a fluid flow that's rotating around a center. And so we have only angular velocity. And we consider that it is rotating, that the background fluid is rotating in the counterclockwise sense. And for the profile of the velocity, we consider this expression proposed by Rosenhead. So we consider this expression proposed by Rosenhead, and this expression is inspired by the profile observed in the experiments. We could have a more realistic expression, but in general, these more realistic expressions depend a lot on the initial conditions and the boundary conditions of the system, and they can have kind of sharp edges. So in this case, this expression has a smooth dependence on the radial coordinate. So it's better to do the computations, but it still presents a profile that has a background vorticity, a non-zero vorticity. So for this fluid flow, we can find we can find the limits of the ergoregion by considering the radius for which the Mach number is equal to 1. So when the velocity, the angular velocity, is equal to the speed of sound, and we find this expression for the inner and outer radius of the ergoregion, and this depends on this alpha, which is a dimensionless circulation parameter. And dc is also related to the circulation. And this r0 is the radius of the vortex core. So when this alpha is larger than 2, then we can have both an outer and inner radius for the ergoregion. But for when alpha is equal to 2, then we have only then in this case the ergoregion is just a circle. Is just a circle. We redefine our uh, quantities using this radius of the vortex core and also the speed of sound. And here we have the Mach number in terms of this dimensionless radius component. And we can see, and so here it's easier to see what I was telling you about. So for alpha equal to 2, you have only one value of the position for which the Mach number is equal to 1. So in this case, your ergoregion is just a circle, or in other words, you don't actually have an ergoregion. Corresponds to the extremal case. But for alpha larger than 1, then larger than 2, sorry, then you can have an outer and inner radius for the ergoregion. And okay, and the radius core, it's located between this outer and inner radius. In here, you have the vorticity in terms of the radial position. And we see that the vorticity is also a smooth function of the position. So it has its maximal value at the x equal to 0, and then decays as we go to larger values of the position. So in order, we are going to compute the quasi-normal modes for the solution. In order to do this, we consider this expression for the field, and we find this radial equation that we have to solve considering the appropriate boundary conditions. Since we are going to study these quasi-normal modes, then we consider a boundary condition at infinity that corresponds to an outgoing mode, and we consider an inner boundary condition at some position at an inner radius. And this boundary condition for this case, it's a Neumann type boundary condition, and it represents a cutoff in the radial velocity of the perturbation. We chose these boundary conditions because it's somewhat easier to implement experimentally, since it corresponds to higher values of the impedance. So in order to find these quasi-normal modes, we consider two different methods. We use the direct integration and the continued fraction method. So for the direct integration, we consider these ansatz for the field, and then we integrate inward from from infinity to this inner radius where we impose the boundary condition. And then we use a root finding method to see for which frequency this inner boundary condition is obeyed. So we also use the continued fraction method. So in this case, we consider this expression for the field, and we find these recurrency relations that are shown there. And we have, and this alpha, beta, gamma, and so on, they are the recurrence coefficients that I'll not show you here, but they depend on the frequency of the modes. And we have to apply 8 Gaussian eliminations in these expressions, and we find this three-term recurrency relation. Manipulating this equation. So manipulating this equation and considering the inner boundary condition, we can find this minimal solution. And then we can use, again, a root finding method to find which frequency that obeys this expression. We compare the results that we obtained using these different methods. So this is for the direct integration, this for the continued fraction, and we find that this both methods show very similar results for both the stable and the unstable solutions. So here we present the reflect real and imaginary part of the quasi-normal modes. For this, in this case, is for the extremal case, so for alpha equal 2. And in this case, since we are in the extremal case where the ergoregion is just a circle, then we don't have any unstable mode. So the imaginary part is negative for the values of the position. In this case, the position of the where impose the boundary condition, which is an inner radius. Here represent the same thing, but for alpha equal to 4. So in this case, we have an inner outer radius for the ergoregion. So we have an ergoregion, and we have now modes that have a positive imaginary part. So we have unstable modes for this case. Here represent the real imaginary part of the quasi-normal frequency, quasi-normal mode frequency, but for different values of the circulation parameter. And here you can see that as we increase the values of n, then the threshold between the stability and instability increases. So this happens because this instability is a phenomenon that happens for larger values of n. So it takes over for larger values of n. In this case, we plot the real imaginary part of the frequency in terms of the radial the original radial coordinate, and we do this because now we want to see we want to compare the irrotational and the rotational cases. So here, for when the radius of the vortex core is equal to 0, then we are in the irrotational case. So we can see that when for the irrotational case, which corresponds to this red line, the imaginary part is larger than for the rotational cases, which are this blue and black dotted lines. So this indicates that the vorticity tends to diminish this instability. Here we plot the solution for the alpha in terms of the dimensionless position. And these lines, they separate the stable and unstable mode. So this corresponds to the frequency equals to 0, which separates the stable and unstable modes. What we see here is that when the n is larger, then these curves approach the case for alpha equal to 2, which is the extremal case when you have just a circle instead of an ergoregion. So this is also a consequence of this dependence of the phenomena of higher values of n. So basically, what we can see from this plot is that you have a larger number of modes that can be that are unstable when you increase the value of n. So to summarize, we studied the Ergoregion stability for a system with vorticity, and this is interesting to do because we now have lots of we have in the last years been seeing more of these experiments being made in the laboratory, and we see that we need to consider more realistic situations. So when we are far away from the Ergoregion or from the acoustic horizon, then it's more or less okay to ignore the effect of the vorticity. But as we get closer to this region, to the center of our system, then this vorticity starts to play a more relevant role. So it's interesting for us to see what is the effect of this vorticity in this kind of systems. And this instability can occur in any system that has an ergoregion but has no event horizon. So this is what we study here. And the ergoregion stability is a large M phenomenon, as I just said, and this vorticity tends to diminish as the instability tends to diminish the instability of the system. Just to make a little bit of shameless propaganda. So in a few days, we are going to have the first Gravitas School on Gravity and Fields in Salinopolis. We'll have seminars, short courses, and I hope to see everyone there. Thank you for your attention.
Okay, thank you very much, Carolina. So now time for questions. Please come here, Carlos.
Thank you, Carolina, for the nice presentation. I was wondering, so in this model do you have closed null trajectories, closed, um, well, light rings, um, in this effective geometry? You do. Do they come in pairs? Do you have a stable and an unstable one? That's my question. And, okay. Could you have a situation, you see, if it would be just, so you have an inner boundary condition, right? So that kind of gives it a sort of non-trivial topology. Otherwise, the existence of an ergoregion would actually imply the existence of those trajectories, and they should come in pairs in that case. And I was wondering also if you could have a situation where there is no ergoregion, but already those trajectories. And then if there would be any impact on your quasi-normal modes, especially for large M of those trajectories, especially the stable one. Um, all had already the light rings, which would happen in some situations for this would be like an echo, right? But again, you have a non-trivial topology because they're inner boundary condition. But then, I mean, models like this are interesting to, just to test some of these ideas about the existence of these orbits and their impact, and especially for modes with large M. Okay, but maybe we can discuss a bit more afterwards. Thank you.
Okay, more questions? So more questions for Carolina. I have one question from a layperson in the field, which has to do with this black hole bomb that you mentioned in the beginning and this mirror. So is that physical, or is that what is the physical? In nature, how could that be realized?
Okay, so the mirror isn't physical, but you can have something that will give this trapping condition at some larger radius. So, for instance, you can have, if you have a massive field, then this mass will act as kind of kind of the mirror, so something that will keep these motes trapped around the black hole.
Okay, thank you. So one last chance for question to Carolina. So if not, let's thank Carolina again and let's move on.